In this video, we're gonna study the dual simplex method. Let's start by recalling the proof of the strong duality theorem. In this proof, we considered our primal linear programming problem in standard form and the corresponding dual problem. Then we considered the simplex method applied to the primal. We defined a dual vector P transposed defined as CB transpose B inverse. And we noted that the primally optimality conditions coincide with the dual feasibility conditions. To see this, we only needed to substitute CB B inverse in the definition of reduced costs with our vector P. So far, we always thought of the simplex method as an algorithm that maintains primal feasibility and works towards optimality. Based on our observation, now we can say that the primal simplex method equivalently maintains primal feasibility and works towards dual feasibility. A method with this property is also called a primal algorithm. An alternative is to do exactly the opposite. We could start with a dual feasible solution and work towards primal feasibility. A method of this type is called a dual algorithm. The dual simplex method that we study in this video is a type of dual algorithm, and we will see it implemented through the full tableau. We will see that the dual simplex method solves the dual problem, and geometrically it will move from one basic feasible solution of the dual problem to another one. Similarly to what we saw for our original simplex method, also called the primal simplex method, one can implement the dual simplex method also in a naive fashion or by keeping track of the inverse of the basis matrix. In this latter case, we obtain the revised dual simplex method. I'm not going to discuss it, and if you want to know more, look at exercise 4.23. So now let's introduce the dual simplex method. As always, we start from a primal linear programming problem in standard form, and we constructed the corresponding dual. As always, we assume that the constraint matrix A has linearly independent rows. Once again, we consider a basis matrix B. Recall that B consists of m linearly independent columns of A. We can now use the basis matrix B to construct the corresponding tableau. The tableau that we obtain is nothing new. In fact, it's exactly the same tableau that we had in the primal simplex method. In particular, our basis matrix B defines a basic solution to the primal problem, and the corresponding basic components are given by B inverse B, as usual. But the matrix B also defines a dual vector, and we know very well that this dual vector is P transpose equal to CB transposed B inverse. Now, the tableau that we have constructed is nothing new. The only difference is that here we don't require B inverse B to be non-negative. So our primal solution is a basic solution, but it's not necessarily feasible. On the other hand, we make an assumption that we didn't make in the primal simplex. Namely, we assume that the reduced costs are greater than or equal to 0. We know that requiring the reduced cost to be non-negative is equivalent to saying that P satisfies P transposed A less than or equal to C transposed. Therefore, our dual solution is feasible. Now we can look at the cost of our dual feasible solution. This is P transpose B, and by replacing P with the CB B inverse, we obtain that the cost is CB transposed B inverse B, and now we can replace B inverse B with XB, and we obtain that the cost is CB transposed XB. So the cost of our dual feasible solution is the negative of the entry at the upper left corner of the tableau. Now consider two separate cases. In the first case, we have that B inverse B is greater than or equal to 0. In this case, we also have a primal feasible solution. Such a solution has the same cost as our dual feasible solution. This means that both our primal and dual solutions are actually optimal, and so there's no need to continue with our simplex method. The second case is when B inverse B has some negative components. In this case, we need to perform a change of basis. To perform a change of basis, we find some index L such that XPL is strictly negative. Then we look at the nth row of the tableau. which is called our pivot row. The entry in the first column will be the lth component of B inverse A1, and so on and so forth. This row contains all the lth components of the vectors B inverse AI. Let's denote these components by V1 until Vn. Now, for every Vi that is strictly negative, we form the ratio C bar I divided by the absolute value of Vi. We select the index j for which this ratio is the smallest. In particular, this means that Vj is strictly negative and C bar j divided by the absolute value of Vj is the minimum of all the ratios C bar I over the absolute value of V bar I for every I with Vi negative. Now the entry Vj is called the pivot element, and the jth column of the tableau is called the pivot column. We can immediately observe that the variable xj is non-basic, because basic variables have unit vectors in the corresponding columns, while here Vj is a strictly negative number. Next, we perform the change of basis. We will have Aj enter the basis and Abl exit. The change of basis is now performed exactly as we did in the primal simplex. We add to every row of the tableau a multiple of the pivot row so that all entries in the pivot columns become 0 except for the pivot element which is set to 1. In particular, also the reduced cost C bar j has to become 0. This means that we multiply the pivot row by C bar j divided by the absolute value of Vj, and we add it to the 0th row. If we look at the reduced costs, the new reduced costs of the variable xi will be C bar I plus Vi times C bar j divided by the absolute value of Vj. Now that we've understood what happens to the reduced costs with our change of basis, we actually understand why we define the index j as we did. In fact, this choice of j allows us to obtain a 0 instead of C bar j, while keeping all the reduced costs non-negative, which we need to maintain dual feasibility. Of course, you should prove this statement. It should be clear from our discussion of this change of basis that the changes of basis for the dual simplex method and for the primal simplex method are very similar. However, there are some key differences, and it's important to always remember them very clearly. One key difference is that while in the primal simplex we first choose the pivot column and then the pivot row, in the dual simplex we first choose the pivot row and then the pivot column. Another key difference lies in how we constructed the ratios. In the primal simplex we look at the positive entries of the pivot column, while here we look at the negative entries of the pivot row. Accordingly, also the ratios are calculated differently, especially because in the denominator here we have the absolute value of the entries in the pivot row, while in the primal simplex the entries in the pivot columns were already positive, so in the ratio we didn't need to have in the denominator the absolute value. Let's immediately see a small example. Let's say that in our dual simplex method we currently have the tableau over here. It's immediately clear from this tableau that we are using the dual simplex method and not the primal simplex method. In fact, I have a negative entry in the 0th column, and I have all reduced costs greater than or equal to 0. So now the second basic variable is strictly negative, so we choose the second row to be the pivot row. We need to look at the negative entries of the pivot row, and these are -2 in the second column and -3 in the third column. We compute the corresponding ratios, which are 6 divided by 2 and 10 divided by 3. The smallest is 6 divided by 2, and so we have that the second column should enter the basis. Next, we need to perform the pivot. We need to obtain 0, 0, 1. To obtain a 0 in the 0th row, we multiply the pivot row by 3 and add it to the 0th row. To obtain a 0 in the first row, we multiply the pivot row by 2 and add it to the first row. And finally, to obtain a 1 in the pivot element, we divide the pivot row by -2. If we perform these operations, we obtain this new tableau. As you can see, the cost was 0 and has now increased to 3. All the reduced costs are still greater than or equal to 0, so we still have a dual feasible solution, but now we also have that B inverse B is greater than or equal to 0. So we also have a primal feasible solution with the same cost, and so we have found optimal solutions. Now let's discuss termination. In our pivot column, we have that Vj is strictly negative and C bar j is greater than or equal to 0. First, let's assume that C bar j is strictly positive, because this will make our discussion much simpler. In this case, when we perform our pivot, we need to replace the positive C bar j with a 0. And to do so, we need to add the positive multiple of the pivot row to the 0th row. Now, since our XBL is strictly negative, this elementary row operation has the effect of adding a negative quantity to the upper left corner in our tableau. This means that the dual cost increases. So, if C bar j is strictly positive for every non-basic variable, then the dual cost increases with each basis change. And this directly implies that no basis will ever be repeated throughout the dual simplex algorithm. This guarantees that the dual simplex algorithm must eventually terminate. Based on our discussion, the algorithm can then terminate in one of two ways. The first case is when we end up in the 0th column with B inverse B greater than or equal to 0. This means that we found an optimal solution. The second case is when all the entries v1 until vn in the pivot row are non-negative. This means that we're not able to choose a pivot column and a pivot element. In a way that is symmetrical to what we saw for the primal simplex method, this implies that the optimal dual cost is plus infinity and that the primal problem is infeasible. I refer you to exercise 4.22 for a guided exercise about this. We're now ready to provide a summary of our dual simplex method. In a typical iteration, we start with the tableau associated with the basis matrix B and with all reduced costs non-negative. Next, we examine the components of the vector B inverse B, which are the entries in the 0th column of the tableau. If they're all non-negative, we have an optimal basic feasible solution and the algorithm terminates. Otherwise, we choose some L with XBL strictly negative. Now we look at the nth row of the tableau. This row has elements XBL, V1 until Vn. If all the VI's are greater than or equal to 0, then the optimal dual cost is plus infinity and the algorithm terminates. Otherwise, for every I with Vi strictly negative, we compute the ratio C bar I divided by the absolute value of Vi, and we define J to be the index of a column that corresponds to the smallest ratio. The column ABL then exits the basis and the column AJ takes its place. Then we add to each row of the tableau a multiple of the nth row so that Vj becomes 1 and all other entries of the pivot column become 0. Now let's get back to the issue of termination. The case that we haven't yet discussed is when the reduced cost C bar j in the pivot column is 0. In this case, the 0th row of the tableau doesn't change at all, and in particular the dual cost remains the same. So our previous proof of termination doesn't work. And in fact, in this case, the algorithm can cycle. Also for the dual simplex, this can be avoided with a suitable anti-cycling rule. Also for the dual simplex method, one anti-cycling pivoting rule can be obtained from the lexicographic order. In this slide, we have the definition of the lexicographic pivoting rule for the dual simplex method. We have complete freedom on the pivot row, so we choose any row L such that XBL is strictly negative. Then we determine the index J of the entering column as follows. For each column with Vi strictly negative, we divide all the entries of the column by the absolute value of Vi, including the entry in the 0th row. And then we choose the lexicographically smallest column. If there is a tie between several lexicographically smallest columns, then we're supposed to choose the one with the smallest index. Now I leave it to you to compare this lexicographic pivoting rule with the corresponding one for the primal simplex method. The most important difference here is that while in the primal simplex method it was not possible to have any tie between the lexicographically smallest rows in that case, in the dual simplex method it can indeed happen that you have a tie between several lexicographically smallest columns. And this is why we have here a sentence that tells you how to break the tie in such a situation. Also for the lexicographic pivoting rule for the dual simplex method, we need to initialize the simplex method in a specific way to avoid cycling. Namely, we need that every column of the tableau is lexicographically positive. In this setting, the lexicographic pivoting rule guarantees termination in a finite number of steps. The proof is largely similar to the one that we saw for the primal simplex method in Theorem 3.4 and is left for you as an exercise. Now we have fully understood the dual simplex method. So we have seen in chapter 3 the primal simplex method and now in chapter 4 the dual simplex method. But when is it better to actually use the dual simplex method? One case is when a basic feasible solution of the dual problem is readily available. In fact, in this case, we can immediately start using the dual simplex method starting from such a solution. On the other hand, if we use the primal simplex method, we would have no use for such a basic feasible solution of the dual, and we would have to run first phase 1 to find a basic feasible solution of the primal, and then phase 2. So essentially, using the dual simplex method, we skip phase 1. A very important setting where it happens that we have a basic feasible solution of the dual problem arises in the following situation. Suppose that we have solved a linear programming problem, so we have an optimal basis for it. Now let's assume that we want to solve the same linear programming problem but with a different right-hand side vector b. Now the optimal basis for the original problem could be primal infeasible under the new right-hand side vector. This can be seen directly by looking at the constraints of the primal that are ax equal to b and x greater than or equal to 0. In particular, these constraints depend on the right-hand side vector, so by changing it, your basis might become primal infeasible. On the other hand, our old basis still remains dual feasible. And this can be easily seen by just looking at the constraints of the dual, which are p transpose A less than or equal to c transposed. As you can see in this system of inequalities, the right-hand side vector b doesn't play any role. Therefore, even if we change it, our old basis remains dual feasible. So in this case, when you want to solve the same problem for a number of different right-hand side vectors b, it's definitely quicker to use the dual simplex algorithm starting from the optimal basis for the problem that you've already solved. Next, let's discuss the geometry of the dual simplex method. To discuss the dual simplex method from a geometrics perspective, let's recap a couple of concepts that we've already seen. As usual, our primal is in standard form, and we assume that the matrix A has linearly independent rows. Let's now pick a basis matrix B whose columns are AB1 until ABM. We know very well that this basis matrix determines a basic solution to the primal, and such a solution has basic components xb equal to b inverse b. We also know that the same basis can be used to determine a dual vector p. This can be done by looking at the equality constraints p transposed abi equal to cbi for every I from 1 to m. So these are a total number of m equations in m unknowns, because our vector p has m entries. Since the columns AB1, ABM are linearly independent, this system has a unique solution that we call P. Now the equality constraints that we considered were obtained by setting to equality m constraints in the dual. So for our dual vector P, the number of linearly independent active dual constraints is equal to the dimension of P. So our vector P is a basic solution to our dual linear programming problem. We can also write down in matrix notation what is exactly our p vector. In fact, the system of equalities can be written as P transpose B equal to CB transposed. By multiplying on the right by B inverse, we obtain that P transposed is equal to CB transposed B inverse. So P is a basic solution to the dual. If P also satisfies P transposed A less than or equal to C transposed, then P is a basic feasible solution of the dual. So to recap, a basis matrix B gives rise to a basic solution to the primal and a basic solution to the dual. In our dual simplex method, the vector P always satisfies P transposed A less than or equal to C transposed. So in the dual simplex, P is always a basic feasible solution to the dual. So far, our geometric interpretation has always focused on the primal. Now instead, we're going to focus on the dual. Hence, we're going to focus on the fact that at every iteration we have a basic feasible solution to the dual problem. Now let's consider two consecutive iterations of the dual simplex. In these two consecutive iterations we have m-1 linearly independent active constraints in common. This is because in our basis matrix B we change only one column. This implies that in our two consecutive iterations the basic feasible solutions to the dual are either adjacent or they coincide. Let's see now an example to visualize this concept. On the left we have our primal in standard form, and on the right the corresponding dual. Now the dual problem is easy to visualize because it has only two variables. On the other hand, the primal has four variables. However, the variables x3 and x4 are just the surplus variables, and so we can eliminate them to obtain an equivalent two-dimensional problem. So we remove x3 and x4 and replace the equality constraints with greater than or equal to constraints. Here they are. Now we can visualize both the primal and the dual problem. Of course, the primal is not exactly the problem we started from, but it can be shown that the geometry of the two problems is essentially the same. If you're interested in understanding this better, I leave to you as an exercise to understand what exactly I mean and how to show it. So here we have pictures for our primal and our dual. On the left we have our primal and the feasible region is the one in gray over here. On the right we have the dual and the feasible region is again the shaded area. Let's first focus on the primal. You can check that there's a total of 5 different bases in our standard form primal. Correspondingly, we have 5 different basic solutions. These 5 basic solutions are A, B, C, D, and E in our picture. The same 5 bases also give us 5 basic solutions to the dual. In the picture they are A, B, C, D, and E. Let's look at one of these bases, the one formed by the columns A3 and A4. The corresponding primal basic solution is obtained by setting x1 and x2 to 0, and the primal basic solution that we obtain is 0, 0, minus 2, minus 1. In our two-dimensional picture of the primal, remember we threw away x3 and x4, so this is the point 0, 0, which is the point A. Now let's construct the corresponding dual basic solution. To obtain it, we need to set to equality the third and fourth inequality constraints of the dual. If you solve such a system, you obtain the basic solution 0, 0. So in the dual, we obtain the vector A equal to 0, 0. Note that the primal basic solution that we obtained is not feasible, while the dual basic solution that we obtained is feasible. This means that we can use such a basis to start the dual simplex method. You can check that this is the initial tableau that we obtain. Note that it's clear that this tableau is being used for the dual simplex method because all the reduced costs are non-negative, and in the zeroth columns we have negative entries. Now let's perform the dual simplex. We select the negative entry minus 2, and so the first row of the tableau is the pivot row. We compute the ratios 1 divided by 1 and 1 divided by 2. The smallest one is achieved by x2, which then determines the pivot column. If you now perform the pivot, you obtain the tableau at the bottom of the slide. We still have a negative entry in the zeroth column, and so the second row is the pivot row. There is only one negative entry in the pivot row, so the first column will be the pivot column. We now perform the pivot and we obtain the tableau on the top of the slide. Now the entries in the 0th column, except for the 0th row, are all greater than or equal to 0. This means that we found a primal basic feasible solution, which is therefore also optimal. And the dual simplex terminates. Now the sequence of tableaux that we've obtained corresponds to the path A, B, C. So let's have a look at this path both in the primal and in the dual. In the primal we started here, at the next iteration we were in this point and ended up in our optimal solution C. So in the primal space, the path traces a sequence of infeasible basic solutions until it becomes feasible at the very end when you find an optimal solution. Now let's look at the same path in the dual. We started in A, went to B, and ended up in the point C. So in the dual space, the algorithm behaves exactly like the primal simplex method. It moves through a sequence of feasible solutions in the dual, and at every step it improves the cost function. Based on this geometric understanding, it is tempting to say that the dual simplex method is just the primal simplex method applied to the dual. However, this is not entirely correct, and this is because the dual problem is not in standard form, while the primal simplex can be applied only to standard form problems. Of course, you can still convert the dual problem into standard form and then apply the primal simplex method. However, the resulting method that you would obtain is not necessarily the same as the dual simplex method. You can find more details about this in exercise 4.25. So what is the dual simplex method visualized on the dual? Well, we can say that it's a variant of the simplex method which is tailored for problems defined only in terms of linear inequality constraints. The last topic that I want to discuss in this video is duality and degeneracy. The first thing we want to do is understand what is dual degeneracy. As always, consider the setting where we have a standard form problem in which the row of the matrix A are linearly independent. We know very well that any basis matrix B leads to an associated dual basic solution given by P transposed equal to CB transposed B inverse. To understand degeneracy, we need to understand the active constraints at P. The dual constraint P transpose Aj equal to Cj is active if and only if we have Cb B inverse Aj equal to Cj, where we only replaced P using this formula. So the jth constraint is active if and only if the reduced cost C bar j is 0. Now our vector P has dimension m, so dual degeneracy amounts to having more than m reduced costs that are 0. We already know that the reduced costs of the m basic variables is always 0. Therefore, dual degeneracy happens whenever there exists at least one non-basic variable that has a reduced cost of 0. Since the reduced costs are also present in the 0th row of our tableau, it's also very easy to understand degeneracy directly from the tableau. Next, we're going to see an example that deals with the relation between the degenerate solutions in the primal and in the dual. Our primal problem in standard form is on the left, and on the right we have the corresponding dual. As in the previous example, we want to visualize both problems. The dual can be easily visualized because it has dimension 2, and to visualize the primal we drop x3 and x4, which are just surplus variables. So we obtain the new primal that has only two variables and is no longer in standard form. Now we can visualize both problems. On the left we have our primal problem, and on the right we have our dual problem. Now you can check that we have a total number of 6 different bases in our original standard form problem. However, these 6 different bases lead to only 4 distinct basic solutions in the primal, and these are our points A, B, C, and D. However, in the dual, the 6 bases lead to 6 distinct basic solutions. These are A prime, A double prime, B, C, and D. To understand better this situation, let's look at the bases formed by the columns A3 and A4. To obtain the corresponding primal basic solution, we need to set x1 and x2 to 0. So we obtain point A. To obtain the corresponding dual basic solution, we need to set the third and fourth inequalities to equality, and if you do so, you will obtain the point 0, 0, which is point A in the picture in the right. So this basis leads to an infeasible basic solution in the primal and to a basic feasible solution in the dual. Now let's look at the basis formed by the columns A1, A3. You can check that also this basis leads to the primal basic solution A. On the other hand, the corresponding dual basic solution is the point A prime, and this vector is a basic feasible solution to the dual. Finally, consider the basis formed by columns A2 and A3. You can check that once again in the primal we obtain the basic solution A. On the other hand, the corresponding dual basic solution is 0, minus 1, which is point A double prime in the dual. And this basic solution in the dual is infeasible. So in this example, we have seen that three different bases may lead to the same basic solution for the primal, but to different basic solutions for the dual. We've also seen that out of all the different basic solutions in the dual that we obtained from this basis, some were feasible and some were infeasible. Finally, I want to conclude this video with a little summary of some of the main properties of basis and basic solution that were discussed in this section for standard form problems. Every basis determines a basic solution to the primal and a basic solution to the dual. And the basic solution to the dual is defined by P transposed equal to CB transposed B inverse. We can understand if this basic solution is feasible by looking at the reduced costs. It is feasible if and only if all the reduced costs are non-negative. To understand the active constraints in the dual problem, we only need to look at the reduced costs. The active constraints correspond to the reduced costs that are equal to 0. This allows us to understand if our dual basic solution is degenerate. It is degenerate if and only if some non-basic variable has 0 reduced cost. With this summary, we conclude our video on the dual simplex method.